Do we have sound? I think we do have sound. Good, thank you. Well, as you're probably aware, this class is live streamed at paradoxes.org. So, look good when you're on camera here, okay? And also, we're uploading all of the notes and handouts at paradoxes.org. I did not bring my usual several hundred copies of these with me today. I'm trying to encourage you to go to paradoxes.org. And so just to review, you will see at paradoxes.org the questions that we're going through in the book of Isaiah. You'll also see all the passages in the book of Isaiah that deal with the Trinity. Remember, 3 of the questions focused on what Isaiah says about the doctrine of the Trinity. And thank you. This handout, which is by the way, it was just this week on Twitter. Into my Twitter page in several days because I got a deadline I'm trying to meet. And I just heard from Mark here that I got hundreds, at least 100 different responses on one little tweet I put up about evidence for God. Evidently, a lot of people don't like the idea that God exists. So I'm going to have to get caught up and engage all these folks. So thank you for the exhortation. Hey, Hugh, you need to be ready. There's a lot of people taking shots at you here. So I'll do what I can. In fact, I was just talking with Ross beforehand. When you're on social media, how do you know when it's just a troll that's just spewing out anger and isn't going to listen, with someone who's spewing out anger but really has a chance to listen? Again, I just ask them questions, okay, and give them links. And my test is if they keep ignoring my links, and one often thing that says, oh, you just want me to go to the link because you want to make money off your books. And so I made the point, look, I don't get a dime from any of the sales of my books. That all goes to Reasons to Believe, not to me at all. So I have no financial incentive. Moreover, we're giving away free chapters of all of my books. And if they won't even get the free chapter, if they won't get the free article, then it tells me they're really not prepared to listen. They just want to blast off. They're just angry. But it's amazing to me how many people portray themselves as angry atheists and actually can be quite insulting and use foul language on Twitter. Twitter allows you to do that. Facebook doesn't, but Twitter does. That often they're open and they're just looking for someone who's actually going to seriously engage them. And so I've seen a number of these folks really change their whole demeanor and begin to engage. So you never know until you put them to the test, and you have to be ready to do that. So, okay, going back to paradoxes.org, you'll also find this little thing on the end of the universe passages. And what I meant to say was that a couple of atheists who come from a Jewish background were quite incensed that I suggested that the book of Isaiah teaches a doctrine of the Trinity. And they said, that's a Christian myth that Isaiah teaches a doctrine of the Trinity. I said, well, have you actually read the book of Isaiah? Oh yeah, I've read the book of Isaiah. Then you just pose a couple of questions, and it's quite clear they really haven't read through the entire book of Isaiah. They know a couple of passages. And so just encouraging them to read through it. But also sending them to paradoxes.org. We actually have these passages listed for you. You can look them, and I'll get to hear your feedback. Never heard from them. So, but yeah. And hopefully they'll be looking at that. But yeah, you'll also find these passages on the time at the end. They're up there. It's about a 4-pager. And let me see what else we got here. Just to review what's up there. Okay. And last of all, we put this up last week. It's the collection of passages that talk about the second rebirth of the nation of Israel. We just got started on this last week. It is up at paradoxes.org. I gave you a homework assignment to begin by looking at all the passages written thousands of years ago that predict that the nation would be reborn, and that happened when the Persians gave the Jews living in the Persian Empire permission to go back to Judea and build their city of Jerusalem, rebuild that, rebuild their temple, and rebuild their nation. And so that rebirth of Israel as a nation flourished for about 5 centuries, and then the Romans came in 70 AD and put an end to the nation and began this dispersion of the Jews throughout the Roman Empire and beyond. But all this was predicted thousands of years ago. We're going to get to that. However, I wanted to give you something that just got released. You're probably aware that over there at the table we have our documentary Journey Toward Creation, where we take you on a journey from the surface of the earth out to the very edge of the universe. And we call it Journey Toward Creation because the farther away you look, the farther back in time you see. And if you look far enough away, you're actually looking at the cosmic creation event. And so we've used this television documentary as a tool to persuade people there really is a creator behind the universe. And the version we have on the table there is in 11 languages. And it's actually been shown on national television in 6 different nations. And wasn't shown on national television in Iran, but we did broadcast it via satellite into Iran, broadcasted it twice, and the people who did it said they got the biggest email response ever from Iranians as a result of seeing that. So it's also it's in Farsi and Arabic, Mandarin, Russian, Japanese, and German, French, and a few other languages. So one of the languages is not on there is Mongolian, but it was shown on Mongolian national television in the Mongolian language a couple of times. What was missing, though, that was produced, a time when I looked a lot younger. A lot of people say, is that really you in that video? Yeah, it is, but it was a few years back. So, but one of the things that was a challenge for us was to come up with images of that part of the journey where you go from the Virgo supercluster out to the edge of the universe. At the time that we produced that documentary, there were maybe half a dozen images that we could throw in. There's now many more images. So one of the things I'd love to see is for us to do a 3rd edition of Journey Toward Creation. And what I want to show you right now is some images that have just been released. And they're public, so you can see these for yourself. What got released was a 176 megapixel image showing you what it's like to go from the Virgo supercluster all the way out to the full extent of the universe. And I'm actually writing a couple of blog articles on this, making the point as you look at these highly detailed images. Because when we did Journey Toward Creation, the images we had beyond the Virgo supercluster galaxies were pretty low resolution. Now they got really high resolution stuff. So, but what I want to do is take you, thanks to these high resolution images, take you, and we're going to make these available at paradoxes.org as well. So I don't know, can you store 176 million megapixels? Maybe not. We'll have to figure out how we're going to make that happen. If it doesn't work at paradoxes.org, we actually created a depository, a library at reasons.org. So worst case scenario, we can send people to reasons.org, and that data bank of images will be there. Well, what I'm going to try to do the next few minutes before we get into Isaiah is take you on a simulated journey from our Milky Way galaxy out to the edge of the universe while we look at these high definition images. And the first one you see here is a map that I created. And I did this because the ones that are available publicly are not to scale. This is to scale. It actually shows you the size of our Milky Way galaxy, the size of the Large Magellanic Cloud and the Small Magellanic Cloud. Those are the 2 dwarf galaxies, the 2 biggest dwarf galaxies that are in the vicinity of our Milky Way. and everything is the correct distance scale and the correct size scale. The Large Magellanic Cloud is about 6% the size of our Milky Way galaxy. But it ranks as the 4th largest galaxy in the local group of galaxies, the galaxy cluster to which we belong. And because of the positions, and there's actually a blog article I've written on this, because of the mass and the size and the position of the Large and Small Magellanic Cloud, they operate as a funnel where they're basically funneling in gas and tiny dwarf galaxies into the core of our Milky Way. You say, what's that red dot there? That's, you are here, okay? That's where we are, that's your address. So that's where we are in the Milky Way galaxy, in between the Sagittarius and Perseus spiral arms. But the Large and Small Magellanic Clouds act as a gravitational funnel, funneling gas and tiny dwarf galaxies into the core of our Milky Way. And if it wasn't for the funnel operating, our galactic arms would collapse and our Milky Way galaxy would become a spheroidal or an ellipsoidal galaxy. And most of the galaxies in the universe are spheroidal and ellipsoidal. And when that happens, basically you get the galaxy collapsing, and now the stars are too close together to make possible the existence of advanced life within that galaxy. If you want advanced life, it's got to be a spiral galaxy. But you can only sustain the spiral structure if you've got a steady flow of gas and tiny dwarf galaxies going into the core of our Milky Way galaxy. Once that flow stops, the spiral arm structure collapses after 3 or 4 rotations. And because we get this steady flow of gas and tiny dwarf galaxies, the spiral arm structure remains stable and highly symmetrical, and that's a requirement for our existence. And people have asked me, do we see any other spiral galaxies in the universe that have got the same mass, the symmetry of the arms, and the spacing between the arms that makes possible the existence of advanced life? The answer is no. They may be there when we look extremely far away. When we look extremely far away, we're looking billions of years back in the past, and that's a time when galaxies like this aren't able to exist anyway. So we don't know of any galaxy that has the features that would permit the existence of advanced life, but our galaxy wouldn't have those features if it wasn't for the Large and Small Magellanic Cloud. Okay, moving a little farther away, this is a map that I've created of the local group of galaxies. And you can see the Milky Way at the lower left there, lower right, and the Large and Small Magellanic Clouds. The Andromeda Galaxy, which like our galaxy comes in at 1 trillion solar masses, so it qualifies as a large galaxy. However, it's not a giant galaxy. There's actually galaxies in the universe that are 1,000 times bigger than our Milky Way galaxy. And so the local group is unique amongst clusters of galaxies in that it has no giant galaxies. And it has only 2 large galaxies. That again is a unique feature. Typically you got a whole lot of large galaxies. Ours is only 2. The 3rd largest galaxy is the Triangulum Galaxy, but it's really not that big. It's big in terms of dimensions, in terms of size, but its mass isn't that great. It comes in a little more than 10% the mass of our Milky Way galaxy. The Milky Way and the Andromeda Galaxy have roughly the same mass. The Triangulum Galaxy is the 3rd biggest galaxy. The 4th biggest galaxy is the Large Magellanic Cloud. The 5th biggest galaxy is the Small Magellanic Cloud. And then the next 2 biggest are those 2 you see on either side of Andromeda. They come in at number 6 and number 7. And in between, we got all kinds of tiny dwarf galaxies. Now, just like we don't see another spiral galaxy sufficiently like ours to be a candidate for advanced life, likewise, we don't see another cluster of galaxies sufficiently like ours to be a candidate for advanced life. When you go to other clusters of galaxies, the galaxies are much closer together. Andromeda is far enough away that it doesn't gravitationally disturb the spiral arm structure of our Milky Way galaxy. Bring it even slightly closer. And by the way, it is heading in our direction. In fact, if you wait another 5 billion years, it will merge with our galaxy. But right now, it's far enough away that it's not disturbing our spiral arm structure. This is what, I got some typical clusters of galaxies here I'm going to show you. And there's about 100 total members of our local group. So you got 2 big galaxies, you got 5 relatively large dwarf galaxies, all the rest are tiny dwarf galaxies. But this is what a typical cluster of galaxies looks like, where you got galaxies everywhere. And incidentally, everything you see there, well, I just see 2 star images. A star image is where you actually see a cross on either side. So where you see that cross, that's a star. If you don't see a cross, you're looking at galaxies. And so what you see there, oh, I see three stars and everything else, hundreds of galaxies. As you can see, they're really giant galaxies. If you want, a galaxy is kind of about the same size as ours. There's one up there. But yeah, you see lots of really big galaxies, lots of large galaxies, plenty of medium-sized galaxies. But the common feature is the galaxies are close together, and hence they're disturbing one another's structure. That's the galaxy cluster Abell 1300. Here is Abell 2744. And this is the core of this. It's actually a really big cluster of galaxies, but this is kind of the core of a cluster of galaxies, where you get an idea. It's loaded with giant galaxies, jammed close together, and they're disturbing the structure of every galaxy in its vicinity. But this is what a typical cluster looks like. Yes?
So in a large spiral, you have 2 nodes that are going around the core and dragging arms around in that pattern. What explains those nodes where the arms attach at the bar?
Okay. Yeah, you get 2 kinds of spiral galaxies. You got those that don't have a bar and those that do. And yeah, they have this, there's a little different structure. Typically, the ones without a bar, you got a lot more gas and stars in the core of the galaxy, which basically breaks up the bar structure. And typically the barred galaxy, the spiral arms are more spread apart from one another. Our own galaxy has a bar, but it's a relatively small bar. There are other galaxies where the bar is as big as the entire spiral structure. Well, you can see a bar at the one at the lower left, and often what that does, it actually causes the arms to merge and form a circle. So you see there a circle and a giant bar. And yeah, I mean, you've got a subtle bar in a spiral galaxy towards the left center. And likewise, yeah, a lot of these are barred. And some of that is just, I mean, it depends on the internal structure. And actually, there's 3 different kinds of barred galaxies that astronomers have studied. But what's unique about our Milky Way galaxy, it does have a bar, and it's a small bar. If it didn't have a bar, we'd be in trouble. If it had a big bar, we'd also be in trouble. So the size of the bar is just right to make possible our existence. And then here's another typical spiral galaxy. And once again, you can just see jammed with hundreds, thousands of galaxies. A typical cluster galaxy has between 1 and 10,000 member galaxies, where you got many giant galaxies, a whole lot of large galaxies, but they tend to be packed quite closely together. I mean, one thing you learn when you take an introductory astronomy class, when you're looking at stars, stars are far apart. I mean, even though our galaxy has 200 to 400 billion stars in it, they tend to be spread far apart. In fact, an analogy I've used in some of my classes to say, if you were to take our star, the sun, which is almost 1 million miles in diameter, and model it down to the size of a grapefruit, the next nearest grapefruit would be in Peru. That's how far apart the stars are. And so stars are relatively far apart, given their sizes. You get the opposite with galaxies. Galaxies tend to be packed quite closely together. But for advanced light to be possible, you don't want giant galaxies in your vicinity, and you want any large galaxy to be far enough away that doesn't disturb the structure. Okay, what I'm going to show you now is a little clip from this 176 megapixel image that's just been released. And here's the first of them. It's looking at the dwarf galaxies that are associated with our Milky Way galaxy. Now, none of this is to scale, okay? These dwarf galaxies are actually a whole lot farther away from a Milky Way galaxy, in which you see portrayed here. What is to scale is the direction of where these galaxies are located, and also and the names are there. So it's showing you all the names. I think there's about 27 dwarf galaxies that are in this particular image. The sizes are not to scale. The distances and sizes are not to scale, but it gives you an idea of the dwarf galaxies that are relatively close to us. By the way, they're all farther away from us than the large and small Magellanic Clouds. And as you can see, they're not to scale either. But it gives you an idea that, yes, the local group is packed with these tiny galaxies. And we're discovering more of these tiny galaxies almost on a weekly basis. Almost every week a paper is published where they say, we found another dwarf galaxy in the local group. Which is good news because the Big Bang creation model was coming under fire because the model that says that the universe is dominated by dark energy and secondarily dominated by dark matter, where the universe has only got about 4.4% ordinary matter in it in terms of its total composition. That came under fire because the model was not predicting the number of dwarf galaxies that we're seeing. The model is predicting that our local group would have 100 dwarf galaxies in it, and a few years ago they said, well, we've only found about 30, and so we got a whole bunch of missing dwarf galaxies. Now astronomers are convinced that we really do have all the galaxies in the local group that the Big Bang, the latest Big Bang creation models predict. It's just that they're going to be difficult to detect. What surprised us is how many of these dwarf galaxies are really diffuse. In fact, we call them ultra-diffuse dwarf galaxies because we're expecting them to be compact and therefore bright enough to detect, but instead they're quite spread out and therefore very difficult to detect. And they tend to not have that many stars. Most of their mass is in the form of gas. That's a good thing because as our Milky Way galaxy eats one of these dwarf galaxies, they're consuming galaxies that are mostly made up of gas and dust. And this is exactly the kind of material you want coming to the core of our Milky Way galaxy to sustain our spiral arm structure. But this again tells us these are difficult to detect. But this is simply making a point. We really are finding them. And as we move out from this, and incidentally, the gentleman that put this all together is Andrew Colvin. So I'm giving him credit here, but he's graciously made these publicly available. And he basically, what he did is he took publicly available high definition images and created a set of images that take you out to the universe. But as we expand away from looking in the vicinity of our Milky Way galaxy, this is his map of the local group. And again, it's not to scale. The Andromeda and the Triangulum galaxies would be much farther away from the Milky Way that you see here. That's why I created for you a to-scale map so you could see. But his goal was actually to show you the member galaxies in the local group that have been discovered so far. And this is why he actually put the galaxies closer together than they really are. So in one image you can actually see all these dwarf galaxies, and you can see there's a whole bunch associated with the Milky Way galaxy and virtually an equal number associated with the Andromeda galaxy, and you actually got some associated with the Triangulum galaxy, and we're anticipating we're going to find a bunch in between the Andromeda galaxy and the Milky Way galaxy. And then moving out again, this is a broad image of the local group. So this is basically showing you all the discovered galaxies so far in the local group. Yes.
Did we see that triangular galaxy when we did the star party?
Is actually quite big in terms of its size, but has a low mass. And so trying to see it through a small telescope just doesn't work.
You can't see it with your eye.
You can't see it with your eye. You can see the Andromeda galaxy with a naked eye. You can't see the Triangular galaxy. I have seen it through my 11-inch telescope, but it's diffuse and very faint. And when I do it on a star party, people look through the eyepiece and say, huh? Because unless you're super dark adapted, you're not going to be able to see the diffuse light, and it doesn't come across as very impressive. So, yeah, and by the way, if you want to ask a question, wait for the microphone. After all, we got a lot of people that are participating through the live streaming. And incidentally, our biggest audience are people who download this class. That's where we jump up into the thousands of participants. But yes, this is Andrew Colvin's map of the entire extent of the local group of galaxies. Now, what is relatively new is astronomers have known for some time that our local group of galaxies is basically on the outer fringe of the Virgo cluster of galaxies, which is a cluster of galaxies that's kind of like what you see in those ones that I've shown you, where you got supergiant galaxies, lots of large galaxies, and they're all jammed tightly together. There's about 3,000 member galaxies in the Virgo cluster. But what astronomers have been able to do is literally map 100,000 galaxies in the vicinity of the local group, and not just map their positions and estimate their masses. They very carefully measured what they call their peculiar velocities. You say, what on earth is a peculiar velocity? That's a term we astronomers use for the velocity of a galaxy where we subtract out the velocity that it has due to the expansion of the universe. And we call it the peculiar velocity because it's basically the velocity of the galaxy that results from its gravitational interactions with stuff in its vicinity, either other clusters of galaxies or nearby galaxies. So these galaxies gravitationally interact with one another, and hence they induce these peculiar velocities. But what astronomers are able to do is to actually make these huge maps of these peculiar velocities of the galaxies, where they subtract out the velocity due to the cosmic expansion of the universe for every single galaxy. And by that means, they're able for the first time to come up with a rigorous, unambiguous definition of a supercluster of galaxies. A supercluster of galaxies is where all the galaxies and galaxy clusters are basically gravitationally interacting with one another. So actually we see velocity flows to a common direction. And then the boundary of these superclusters of galaxies would be those galaxies that are, instead of moving with that flow, are moving against the flow. So this next image was published in the British journal Nature a few years back, and basically talks about this discovery where for the first time they were seeing the boundaries, specific boundaries of a supercluster of galaxy. Now, what's being mapped here are the velocities, not the actual galaxies. You say, what's that little dot there? That red dot represents the position of the local group of galaxies. And that big bright spot you see above and slightly to the left, that's the Virgo cluster of galaxies. So there's where you got thousands of galaxies jammed tightly together. But those yellow lines that you're seeing there are basically showing you the peculiar velocities of galaxies that are moving towards what we call the great attractor. And the great attractor is that point there, that place where you see all the lines kind of converging. In other words, all those velocity lines are moving towards that point where you see those two big bright streams coming together. And a point you actually see a third stream above that comes down to that central screen. That's called the Great Attractor, and that's where we're moving towards, but we're not the only galaxy moving towards that. All the Virgo cluster galaxies are moving towards the Great Attractor, and likewise. And those blue lines, those are showing you galaxies moving away from the Great Attractor. So the basic coming up with a definition of a supercluster of galaxies, it's where you have a gravitational basin, where the galaxies are moving towards kind of a gravitational point or center within the galaxy, and then beyond that boundary, the galaxies are moving away. Yes, we got a question?
You kind of started to answer it, and maybe it looks like not all galaxies are moving away from each other. I always thought that they were all moving away.
Well, with the expanding universe, you've got galaxies moving away from one another, and then what they've done in this map is they've taken out the velocities of each galaxy that's due to the expansion of the universe. So what you're seeing here is a subtracted net result. It's only showing you what they call the peculiar velocities, the velocities due to their gravitational interaction with one another. So they've removed the expansion of the universe from the velocity of every galaxy measured here, and basically showing you, if you take out the expansion of the universe, it actually looks like all these galaxies are moving towards this central gravitational point, the Great Attractor. Okay, question here. Wait for the microphone.
Is it possible that with expansion over 5 billion years, that our horizon or blue line will change? That is, the expansion will overtake the attraction.
Yes, as a matter of fact, the expansion is overtaking the attraction for virtually all the galaxies that we see here. In other words, these galaxies are indeed moving away from one another due to the expansion of the universe. But again, if you take that out, it looks like they're moving towards this central point. They're not really moving. They're not all going to converge into this Great Attractor, because the expansion of the universe completely dominates these peculiar velocities. So yes, don't worry about the fact that we're all going to fall in towards the Great Attractor, because the expansion of the universe is much more aggressive than these peculiar velocities. So actually we're going to see a general dispersion. But what this has allowed astronomers to do is actually determine the boundaries of superclusters of galaxies. And so these blue lines you see here are ones where the peculiar velocities are moving away from the Great Attractor, which means they're moving towards another Great Attractor. So they're basically saying every supercluster of galaxies has got a Great Attractor, where you actually see the galaxies within a particular boundary apparently moving towards that Great Attractor, but it's apparent. It's only there if you take out the expansion of the universe. But it allows for the first time astronomers to actually define the structure of superclusters of galaxies. You know, with a local group, it's easy, because with a local group, the peculiar velocities are actually greater than the expansion of the universe. You remember me telling you how the Andromeda galaxy is actually moving towards our Milky Way galaxy? That's because it's so close to us that its peculiar velocity is actually greater than the expansion of the universe. And therefore, if we wait long enough, those two galaxies will merge together. Matter of fact, the Large Magellanic Cloud eventually will merge with our Milky Way galaxy, again because of the fact that its peculiar velocity is much greater than the expansion of the universe. But I'll tell you this, once you get past our local group, that's no longer the case. Once you get past the local group, the expansion of the universe relative to the peculiar velocity of our galaxy towards those galaxies, the expansion of the universe dominates. That explains why, when we look outside the local group, all we see are redshifted galaxies. All those galaxies are moving away from us, because now you're far enough away. That's another situation. Okay.
That was kind of neat, because I just got back a couple of days ago from a week of observing distant galaxies with my telescope in the White Mountains, and so it was kind of ties right in. I am wondering, this Great Attractor, is that something that we could visualize as being a physical reality or physical entity? And where in the sky, just for informational ideas, would that be?
Well, a lot of people say, I want to look at the great attractor
Yeah.
through a telescope. Really can't do that. It's just so far away. However, what I'm going to show you in the next slide actually is the maps of these clusters of galaxies that are associated with this velocity map. Again, this is not a map of the galaxies. It's a map of the velocities of the galaxies where we've taken out the expansion of the universe. I'll jump to the next slide, and it actually shows you this same, well, what you're seeing here is the entire supercluster that we're part of. It's called Laniakea. They gave it a Hawaiian name, which basically means monster with boundaries. So, yeah, the Hawaiians have these interesting words, and this is all done in Hawaii anyway. But this map basically shows you the region of this Laniakea supercluster of galaxies that's closest to us. So to give you an idea, in this particular point, we're just looking around that red dot. You're looking around that red dot. You're not even going out as far as the Virgo cluster of galaxies. So we're just looking a little bit beyond our local group, and this is what we see. So these are the nearby groupings of galaxies. And what you get to see here is that they're all much bigger than our local group. These are called groups. They're not galaxy clusters as we would normally define them. They're groups of galaxies, or what we call mini clusters of galaxies. But it shows you that the local group, and by the way, that little red dot, that's our Milky Way galaxy. The galaxy you see slightly above and to the left, that's the Andromeda galaxy. So it gives you an idea of the scale. The local group on this particular, 12 feet that you see here of the slide, the local group's extent is about 6 inches. So it just shows you how tiny our local group is. And these other groupings of galaxies are not showing you the dwarf galaxies. They're showing you the giant galaxies, the large galaxies, and the medium-sized galaxies. So in the case of the local group, you only see 2 galaxies. And they don't appear to be very big on this map, because you've got much bigger galaxies in its vicinity. But it does reveal a design feature. We're far enough away from these other much larger groups of galaxies that contain giant galaxies that are jammed tightly together that it doesn't disturb the spiral structure of our Milky Way galaxy. Now, if our Milky Way galaxy were in any one of these other groups, we'd be in trouble. We wouldn't be having this class today. We wouldn't exist. So we have the good fortune of being in a tiny grouping of galaxies that has only got 2 large galaxies in it. And this map basically shows you that's unique. I mean, as we go far away from our local group, we don't see any other candidates, although you do see what's called a great void to the left of our local group. And that's a place where you don't see any galaxies at all. And the problem with if you were to have our galaxy in one of those voids, there wouldn't be enough dwarf galaxies to sustain our spiral structure. Or if there are dwarf galaxies, they'll be too far away to do any good. And so in order to have advanced life, you have to be in a grouping of galaxies. You can't be in one of those voids, but neither can you be in any of these other groups. So again, it just shows you how special our local group is. Now, what I'm going to do is zoom out a little more, and we're still inside the Laniakea supercluster of galaxies. So as we zoom out, get a little farther away, again, a little red dot represents the local group. And now I'm zooming out far enough away that you can see the Virgo cluster of galaxies, which is not the largest cluster of galaxies in the Laniakea, but it's the largest, it's the closest large cluster of galaxies to our local group. And we're considered to be a member of the Virgo cluster of galaxies, but look where we are. We're way out from the Virgo. Virgo's over there at the right with those thousands of galaxies. You see it's packed with giant galaxies and large galaxies, and look how far away we are. And even in between the Virgo cluster of galaxies and our galaxies are really big groups like the M101 group, the M94 group, Canis 2 group, etc. And so, again, we're far enough away that we don't have the gravitational disturbances. And incidentally, if you were to move our local group even as close as where you see the M101 group or the M94 group, we'd now be close enough to the Virgo cluster of galaxies that we would be exposed to the deadly radiation coming out from one of its galaxies, M87. M87 is one of those big spheroidal galaxies in the middle of the Virgo cluster, and it's got a supergiant black hole, comes in at about 7 billion times the mass of our star, the Sun, and it's firing out a jet of very deadly radiation. We're far enough away where you don't have to worry about getting cancer at age 10. Well, I mean, some people do, right? But this would be giving us all cancer at early ages, and fortunately, we're far enough away where that doesn't disturb the possibility of humans reaching adulthood and launching civilization. Then we move a little bit farther away, and now we're actually seeing about half of the Laniakea supercluster of galaxies. Again, Virgo's over to the right, but now we're picking up other big clusters of galaxies like what we see here in Dorado. You can see that now we're picking up a couple more voids. There's a really big void down at the center bottom of this photo, a huge void where you see virtually no galaxies. And again, you can't be in a void. If you're in a void, there's simply not going to be enough dwarf galaxies to sustain your spiral structure. And you can see that there's a void above the local group and one to the left of the local group. But again, shows you just how special we are. Now we're moving out a little farther away, and here you begin to see, oh, just to the right of the Virgo cluster is another cluster, and actually it's the same size. Some people think even bigger than the Virgo cluster. This would be the Centaurus cluster, and you see the Hydra cluster down to the lower right. And now we're beginning to see the overall structure of the Laniakea supercluster of galaxies. In fact, if you remember that velocity map, it showed a big stream of galaxies moving in that direction, then a stream coming down, and you actually see this Pavo cluster up there. That's a really big cluster of galaxies. And that was what you saw to the left. And then as we move out a little bit more, again, you can see this structure beginning to look like that velocity map, showing these big clusters of galaxies relative to where we are in the local group. And now that little dot there is basically encompassing the entirety of the local group. And this actually shows you the entirety of the Laniakea supercluster of galaxies. And so you can see the overall structure of it. Now what's interesting is that this structure we see in our supercluster of galaxies is unlike the structure we see in any other supercluster of galaxies we can map. Using the same velocity technique, we're able to map a whole bunch of superclusters of galaxies around the Laniakea supercluster. But ours is special. It's special in that you see this kind of, instead of seeing all the galaxy clusters kind of jammed together, what you see is they're distributed along these broad arcs, these lines that you see here, and situated in such a way kind of like this and like this, where you've got a protected spot for the local group, rather than having them all jammed together. Okay, again, as we move out from the Laniakea cluster, we begin to see some of the other superclusters that exist. And so this is looking just a little bit farther away from the Laniakea, but you can actually see there's a huge supercluster to the bottom. This actually shows you 5 other superclusters of galaxies that surround the Laniakea supercluster. And then we continue to move out, and you see that once again, this is that little area towards the lower left, just above and below. The Hydra supercluster is part of Laniakea, the Virgo supercluster is part of it, but everything else you see there, these are other superclusters of galaxies. And this kind of structure you see for our Laniakea supercluster, we don't see it. What you see typically is a typical supercluster of galaxies would be like what you see in the Shapley supercluster and the Perseus Pisces supercluster. They don't tend to be spherical, but they tend to be kind of like huge dirigible shaped, ellipsoidally shaped clusters where you've got these millions of galaxies all kind of jammed together in such a way that it permits no room for a cluster like our local group. In other words, if you go to any of these other superclusters of galaxies, it's simply impossible for you to have a local group like our local group where advanced life could exist. And so this is something that astronomers are now just appreciating. Just like our Milky Way galaxy is unique in that we don't see any other that would be a candidate for advanced life, and just like our local group is unique in that we don't see any other small grouping of galaxies sufficiently like ours to be a candidate for advanced life, and just like we don't see a Virgo cluster of galaxies, which allows for the possibility of the local group to exist the way it does, likewise we're now discovering there is no other supercluster of galaxies that's sufficiently like the Laniakea cluster of galaxies that would permit within it the existence of advanced life. Okay, let me move through the rest of this. I mean, this is really incredible. All these maps didn't exist until very recently. But again, it's just showing you, no matter what size scale you look at, you're seeing that everything has been designed to make possible the existence of life. Yeah, wait for the microphone. Can you get the microphone over to Mark here?
Why are there voids and clusters? Why isn't it just spread out evenly throughout the universe?
Well, if you go back to the cosmic, that's a very good question. Why do we have these dense superclusters of galaxies with voids between them? It's basically because of the total mass of the universe and the expansion rate. And this is something that was actually predicted from the maps of the cosmic microwave background radiation. I'll show you a couple of those maps in a minute. But if you remember what those maps look like, you're looking at the universe before galaxies and stars existed, where you got very tiny differentiations between the hot spots and the cold spots of the universe. But actually looking at the cosmic microwave background radiation, you're looking at the universe when it was just 380,000 years old. But because of what we know about the dynamics of the universe, we can actually predict that a particular hot spot will become a future supercluster of galaxies, or a cluster of galaxies, and that the cold spots become the voids. And so this is something that's just happened in astronomy in the last few years, where they've been able to show you these detailed maps. We have galaxies and clusters and superclusters of galaxies. They perfectly match what you would predict from looking at the state of the universe when it was 380,000 years old. And so what you're looking at in the cosmic microwave background radiation are basically different distributions of matter. And it's really tiny. We're looking at probably differentiations of 1 part in 100,000, but that 1 part in 100,000 is enough to predict that, yeah, as the universe expands, you're going to see the cold spots becoming giant voids and the hot spots becoming giant clusters of galaxies and stars. That's one of the great successes of the Big Bang creation model, is that our maps of the very early history of the universe match our maps of the late history of the universe. But let me show you a little bit more here. Here we're zooming out a little bit more distant, and we're seeing that, okay, we're heading towards the Great Attractor, but now we're beginning to see that there is a monster attractor. You read the astrophysical literature, it not only talks about a great attractor, but a monster attractor. And the monster attractor was discovered recently because the direction towards we're headed towards the great attractor is not a whole lot different than the direction we're headed towards the monster attractor. The monster attractor is basically defined by that Pavo Indus supercluster that you see up there. But it's only a slight different direction than the direction we're being pushed or dragged towards the great attractor. And so the great attractor is actually being pulled towards an even bigger attractor. You say, well, is the bigger attractor being pulled to even a bigger attractor? The answer is yes. Wait for it. I'm going to show you. Okay? And again, attractor is really an inappropriate word because the expansion of the universe completely dominates the gravitational movement. We're not really going to be sucked in to this monster attractor. The expansion of the universe is just too much of a dominant component. But now we're beginning to see that our Laniakea supercluster of galaxies is really tiny compared to other superclusters of galaxies. So yeah, we live in a tiny local group, and the Virgo supercluster is really kind of a tiny supercluster of galaxies compared to other superclusters. Then you got the supercluster, which is probably a better name for our Laniakea grouping, and that is also tiny compared to other superclusters of galaxies that we see. And then moving out a little further, we get to see this. This is still looking, there we have our little red dot of where we are. And now you begin to just see how tiny the Laniakea supercluster is. On this particular map, again, we're looking at about, 12 to 15 feet across for the slide. The Laniakea supercluster of galaxies measures about 15 inches total, and yet you see these other superclusters much, much bigger than our supercluster of galaxies. All this, by the way, will be posted at reasons.org. We'll try to post it at Paradoxes if you've got enough storage room to cover it. I'm not sure it's going to work, and trying to get it over there will be a challenge. I couldn't do it with flash drives. We had to do something else.
Any idea what the attractor is made out of?
The super or the great attractor and the monster attractor are made up of clusters of galaxies. So it's basically just giant, compact clusters
So there's
of
not
galaxies.
there's not a big black hole.
Well, each one of these galaxies has a black hole. I'm trying to figure where the microphone is. So over here, okay. Every galaxy has a supermassive black hole, and ours has the unique feature of being a big galaxy with a really tiny supermassive black hole. Our supermassive black hole is slightly less than 4 million times the mass of our star, the Sun. It's a good thing we're not living in the Andromeda galaxy. The Andromeda galaxy has a supermassive black hole that measures between 40 and 150 million times the mass of our star, the Sun. And incidentally, Andromeda is close enough to us if that its supermassive black hole were in an active phase, it would destroy the possibility of us humans having advanced civilization on planet Earth. What's good for us right now, the supermassive black hole and the Andromeda galaxy is in a quiet phase of its history. But in the past, it was much more active. We can see evidence for that. And the future is going to happen as well. We're living in a time window when its supermassive black hole is quiet. And by the way, our supermassive black hole right now is in an exceptionally quiet phase. Again, in fact, I got an article coming out this Monday making the point that our supermassive black hole 1 to 7 million years ago, I think I talked about this when I was here in class last week, is that it was active 1 to 7 million years ago, would have posed a problem for us if we were created that early in terms of trying to launch civilization. And so that's in a quiet phase. But yet every one of these galaxies has a supermassive black hole. There's a galaxy in the Virgo cluster that has a supermassive black hole that is barely far enough away not to cause us trouble. It's about 55 million light years away, far enough away where the radiation doesn't cause us a problem. But if we were closer, we'd be in trouble. Go ahead.
Yeah, I was wondering, is there a purpose for God to create the universe so large and we so small?
Yeah. I mean, You haven't seen the end of it yet, okay? We're not even 5% of the way out to the total extent of the universe. But even this much, I think, is mind-boggling to think about all these gigantic superclusters of galaxies. And as big as our supercluster is, it's tiny compared to these other immense superclusters of galaxies, and there's a whole lot more, which raises the question, why did God have to make such a gigantic universe? Well, if he made the universe any smaller than he did, there'd be no stars in the universe. There'd be no galaxies in the universe. The total mass of the universe determines how rapidly the universe expands. If you don't have enough total mass in the universe will expand so rapidly that gravity will not be able to get the gas in the universe and collapse it to make stars and galaxies. So yeah, a smaller universe, you get no stars, galaxies, and planets, which means you have no possibility for life. That's reason number one. There's a second reason why God made the universe as big as he did. If he made it any less massive than it is, then as the universe expands from the cosmic creation event, there's no opportunity for enough of the primordial hydrogen to be fused into helium where future stars can make elements heavier than helium. So make the universe the tiniest less massive than it is, you get a universe that either has nothing but hydrogen in it or nothing but hydrogen and a smaller amount of helium, a universe with no carbon, no oxygen, no nitrogen, no iron, no phosphorus, and no possibility for life. And you might say, well, what happens if we were to make the universe a little more massive? Make it slightly more massive, then you wind up forming stars that quickly take all that primordial hydrogen and helium and convert it into nothing but elements heavier than iron. Once again, you got a universe with no carbon, no oxygen, no nitrogen, no phosphorus, and no possibility for life. And also, now you got so much mass in the universe that when the universe expands from the cosmic creation event, gravity will collapse that gas into nothing but really big stars. Those stars will quickly burn up and become black holes. So you basically wind up with a universe that's got nothing but black holes and neutron stars. And again, life is impossible. Now, that's a quick answer to your question. If you want a detailed and well-documented answer to your question, it's in the first 4 chapters of why the universe is the way it is. So, but that's one of the amazing things. The universe, as big as it is, has to be that big for physical life to be possible, physical intelligent life to be possible. And to me, that tells me something about our God. Our God loves us so much that he doesn't think it's too expensive to make a universe with all this stuff in it, and actually to fine-tune and design it for billions of years so we can exist at this time. And by the way, even in this map, you're just seeing the tip of the iceberg. We got enough time, I'm going to show you the rest, but let's have one more question, then I'm going to try to get you to the edge of the universe. Go ahead.
I'll need to check. I think it's October, the Carnegie Institution on Santa Barbara Boulevard, which runs the telescopes and Mount Wilson and so forth, opened up to the general public with postdoc astronomers there to answer all your questions. One year I asked, how big is the universe? And the general consensus was, we don't know. And I said, well, what does the mass mean of the universe total? And it says, well, if we don't know the total universe, we don't know the total mass. He says, what's important? He says, the density.
The density is what's important, correct.
Yeah. And then second question is, do we know yet, or is it still unknown in the Big Bang theory of what caused the original temperature fluctuations? I've heard that it's initial gravity and other things, but do we really know the difference of temperatures at 380,000 years?
Well, okay, if we were to go back about 35 years, we had measurements of the cosmic background radiation, which basically told us the temperature that it has today. And we had some spectral measurements that told us what the temperature of the cosmic background radiation was billions of years ago. However, the maps we had at that time could not show the differences between the hot and the cold spots. The COBE satellite was the first satellite that had sufficient sensitivity to actually see the differences in the temperature of different spots in the cosmic microwave background radiation. But astronomers back then knew they had to be there if the Big Bang theory was correct. In fact, that was one reason why COBE was launched, because there were people questioning the Big Bang creation model, saying this model is wrong, there is no creation event, we're mistaken on this, because we're not seeing the temperature differences that the model predicts. And the reason why you would get temperature differences, if you got gravity operating, that's one of the pervasive laws of physics. And you got thermodynamics as a pervasive law of physics. And we have a good entropy measure of the universe, given that entropy measure and the gravity. And then we would expect that we're going to see differentiation long before you get stars in the hot and cold spots of the universe. If there is a Big Bang creation event where the universe expands at a certain velocity from that Big Bang creation event. So 40 years ago, we had a reasonable number for how rapidly the universe was expanding. We knew gravity was a factor, and so if the universe really does have a beginning, 14 billion years ago, then you are going to get these temperature differences. But it was never hard to detect. Well, wait for the microphone.
Do we know why before the light of last scattering 380,000 years ago, perhaps back when quarks became first matter, baryons of neutrons and so forth, do we know anything back in there that there were temperature differences, or what would drive would gravity even be operating there to cause temperature and clumpiness rather than homogeneity where there's smoothness?
Okay. Yeah, you will not get temperature differences until atoms form. Because when the universe is so hot, and see, with the Big Bang creation model, the universe starts off almost infinitely hot. Then as it expands, it gets cooler and cooler. But as long as it's so hot that everything is ionized, where you got nuclei with no captured electrons going around it, you get no temperature differences. Everything gets smoothed out. So you have to wait until atoms form. And atoms do not form until the universe is 380,000 years old. Once atoms form, now you can actually get distinctives between the hot and cold spots. You can actually see where the concentrations of matter are. When the universe is completely ionized, there are concentrations of matter, but you can't see them. So you got to wait until the universe cools enough that atoms form. And so that's when we begin to see it. But those concentrations of mass that are revealed through the temperature differences actually match everything you're seeing here. And that's one of the great successes of the Big Bang creation models, is we see this match. Okay, I'm not sure we're going to get to Isaiah, but I do want to actually get to the edge of the universe, so give me some time to move out to the edge of the universe. So now we're seeing the local superclusters of galaxies. So now we're actually seeing about 100 different superclusters of galaxies. So there you can see, again, in this particular image here, the Laniakea supercluster to which we belong is about 6 inches across. And then you can see all these really big superclusters that surround our relatively tiny supercluster. Hard to believe that the Laniakea supercluster is a tiny supercluster, but it is when you actually look far enough away. Okay, now we're going to zoom out and try to actually see the entirety of the observable universe. So in this next slide, all these little images you see here are superclusters of galaxies. You're not seeing clusters of galaxies. You're only seeing the big superclusters of galaxies. That little red dot there is where we are. And that little red dot encompasses more than the entirety of the Laniakea supercluster galaxies. So now this gigantic supercluster of galaxies in which we reside is reduced to a size that's a lot smaller than that little red dot that you see there. But this slide actually shows you where the great attractor is and the monster attractor. And as you can see above our local supercluster of galaxies, is a whole bunch of really big superclusters. And so actually see, not only is there a great attractor, which is inside our Laniakea supercluster, and a monster attractor, which is just beyond, but there's even bigger attractors. I don't know what terms have come up for them. I haven't seen any in the scientific literature. Maybe just super monster attractors. And so you can see there are several of them right above. But what's interesting is that the great attractor, the monster attractor, and these even bigger attractors are all in the general direction of being above and to the left of where we are. And this explains why in the COBE satellite, the first satellite that had the sensitivity to sea temperature differences, if you look at the raw data, it looks like this. So this is from the COBE, and what they notice is you basically get a dipole feature in the cosmic microwave background radiation, where you see a big cold spot and a big hot spot. And that is there because of the fact that we're being dragged towards these attractors. And so you say, well, how do they get these detailed maps of the cosmic microwave background radiation? They subtract out this dipole effect. They basically subtract out the effect of us being pulled towards these monster, super monster attractors. But this is a feature you see in every cosmic microwave background radiation map, which is why it takes them several months before they're able to publish the maps after they get them, because they very carefully have to subtract out this dipole feature in order to actually see the true state of the universe and its hot spots and cold spots. But getting back to the map here, okay, that's the map I just showed you. And then as we pull away from that, you begin to see, wow, there's a lot more stuff in the universe than anyone ever dreamed of. And here we go out a little bit more. And again, now you see these little faint spots that you see there? Those little tiny faint spots are clusters, superclusters of galaxies as big as the Laniakea supercluster of galaxies. And so once again, we get an appreciation how huge some of these structures are. They look like a speck of light on this particular image, but they're actually really gigantic, much larger, 10, 20 times larger than our Laniakea supercluster of galaxies. And I think it'd be great if we could actually put this in our version 3 of Journey Toward Creation, so you can actually see. I mean, this really gives you an idea of the immensity of the universe. You say, are we all the way out yet? Nope. This gets you out, okay. This is the universe we can see through telescopes, okay, but we call it the observable universe. And by the way, that little red dot there not only encompasses the Laniakea supercluster of galaxies, it encompasses all the neighboring superclusters of galaxies within it and much more beyond. So this is what we see as the observable universe. And here you can see there's big voids. There's lots of superclusters within this, and superclusters all within it. But this kind of gives you a general feel for what the observable universe looks like. Now we call this the observable universe. Steve was pointing out the universe that exists today is actually bigger than what you see here. Because the universe we see through telescopes is the universe of the past. And the universe of the past was smaller than the universe of today. And so when you look 10 billion light years away, you're looking 10 billion years ago, and that's due to the expansion of the universe. The universe was smaller at that point. Okay, 2 minutes. Astronomers have actually calculated the minimum size the present universe must be relative to the universe we see through the telescope. And the answer is at least 48 times bigger. Okay? Now, do you get at least a little bit of appreciation for how much God must love you? That he was prepared to make a universe that big so we could have this special place to live? But the other point I want to drive home is no matter what size scale we look at the universe, whether we look inside our galaxy, look at where the large and small Magellanic Clouds are, look at where we are relative to the local grouping of galaxies, where our local group is relative to the Virgo cluster, where the Virgo cluster sits inside the Laniakea cluster, and where our Laniakea cluster sits within this family of superclusters of galaxies, and where that family sits and within the entirety of the rest of the universe. At each point, we see that we're in a favored location. And, there's something called the Copernican principle in astronomy, which basically is saying Copernicus is right. We're not in the center of the universe. It's a really good thing we're not near any of these really dense clusters of mass. It's important that we be off-center in each point. It's crucial that the Earth be off-center from the Sun, that the Sun be off-center relative to the spiral arms that we see, and that we be off-center relative to the center of our galaxy, we be off-center relative to the center of the local group. In each case, we have to be off-center. So I've actually referred to this as the anti-Copernican principle, is that if you want human beings, we can't be at the center anywhere. We have to be off-center, and we have to be off-center by a very specified degree. And no matter what size scale you look at, you're going to see fine-tuning in the degree to which we have to be off-center. So don't you like the fact that you as a human being are off-kilter and off-center? And, we all have our little quirks. All of our galaxies have their little quirks, but the quirks are just right. And God planned this all billions of years ago. Before he created the universe, he had a plan in mind on how to redeem you from your sin and evil. That he did before he created all this. But I think what blows my mind away is all this has to be created in a just right way so that we can exist and that we can have a possibility of being redeemed from our sin and evil and enter into a virtuous, loving relationship with our Creator and with everybody else. And I think I just used up my 2 minutes. So let me just pray, and I think I'm gone next week. But here's the good news. I got about a 10-week stretch. Maybe it's not good news. There's about a 10-week stretch starting in late November, running through to early February, where I don't have to get on an airplane. So I'll be here for that time. And we will get past the book of Isaiah and jump into another creation text. So, and if you're not aware, the church here has a plan to transform this room and make it into a much more pleasant meeting area where we can actually record messages. And so they've asked me to, in timing, when this is ready, to organize this class. We're basically going to be doing 2 to 8 week series, and they've asked me to bring in a stream of the scholars that are part of our scholar community to do this. I'll still do over half the teaching in this class, but we're going to package everything as messages. And just so you're aware, we're going to change the structure of this class a little bit. We're going to have the first half hour as an uninterrupted talk with all the visuals, and then follow that with 40 minutes of open mic Q&A. Everything's going to get recorded, and we're going to release it as a mini course. And you say, how many mini courses are we going to try to package here? Oh, about 50 or so. So that'll keep us going for a few years. But this is the goal, that this church and Reasons to Believe would actually package a repository of these high-quality mini courses where we want all of you to really get aggressively engaged in the dialogue and the Q&A, because that's going to be the best part. And so if you think of someone who is skeptical, likes to ask questions and challenging questions, hardball questions, bring them here, because that's really going to up the quality of these productions that we're doing. But we're going to keep the class going the way it is right now until they got this room ready to do this, because right now this room isn't structured to enable us to do high quality video recording, but that's our goal. And for what it's worth, every class here is video recorded and it's archived at paradoxes.org. With that, let me close. Father in heaven, we want to thank you for this incredible universe that you created. I personally want to thank you for these astronomers that took the decades of time to develop these amazing images of the distant universe and to reveal to us, Lord, something that really has been unexpected by my peers is that we're off kilter by just the right amount at every stage of the way as we expand our view away from our cluster of galaxies into the vastness of the universe. And Father, I pray we come away from today humbled by what you've done to make possible our existence here on this little tiny planet and the vastness of the universe. Lord, how great your love must be that you did not think it too expensive or too much time to build and construct this amazing universe so we could exist, and we could exist with all the resources we need to develop a huge population on this planet where billions of us can come into relationship with your Son, Jesus Christ, the creator of the universe, but the Redeemer of all of us from our sin and evil. And Father, I pray that you would give us many opportunities, just like you gave Ross on the airplane, where we can share some of these insights and help people realize the magnitude of your love for each one of us and the magnitude of your offer of salvation. In Jesus' name, amen. Thank you.